Welcome to the P1 Classical Mechanics lecture series. So this lecture is called P109.3. So what we are going to do is that we are going to do final two more problems to 109. Okay. So these problems are designed to instigate thinking from your side, right? So instigate the thinking capability with the basic principles. If you don't know the basics, then there is no point in having knowledge, deep vast knowledge about quantum mechanics or cosmological physics or anything like that. Okay, so basics is a foundation and you have to have the basic foundation. So the first problem, I'm going to do the first problem anyways. So the first problem is like this: you have a circular conical uh, funnel. Okay, a conical funnel just like that. Okay, it's rotating around. Okay, and there is a ball. There's a ball like this and it is rotating around this funnel. Okay, so you can imagine that it is rotating around this funnel. Okay, and the things that I have is that the mass of the ball, and I have two balls, just say that I have two balls. So mass of the first ball is 10 kilograms and mass of the second ball is 5 kilograms. Okay, two balls, and the velocity of these balls, okay, each balls is 10 meter per second. Okay, 10 meter per second. All right, and the slant angle of this cone, okay, the angle of this cone is some theta degrees, and theta must be equal to 45 degrees. These are the things here. Now I need to find out for these 2 kiloweights of balls, right? Two balls are there. The first one is 10 kilogram and the second one has 5 kilogram. And would there be any difference in the radius, okay, in the radius of rotation for these two balls? Okay, the radius of rotation for these different masses, that's the question. So you can do this, you can pause this video and do the problem yourself, or if you don't know how to do it, then let's do it together. Okay, so the first thing I can do is that I can take the situation here. Okay, situation here, and then I can draw the force, right? Force diagram. The first force is the gravitational force, which is mg for general mass, mg, and the second force here is the contact force, normal force. Okay, and we have know the angle theta. Okay, so that's very clear. Now what I can do is that, as always, you can resolve the components of normal force. Right? Normal force components can be resolved into x and y axis, right? So there is ny and nx. Now the problem is I don't know the angle, so I cannot resolve without the angle. I cannot resolve using trigonometry without any angle. So let's have a look at the situation just like this. So this is the theta here. Okay, there is no doubt about that, and let's call this angle alpha. Okay, the normal force just looks like that. Okay, so let's call this side some x. Okay, angle x. So if that's the case, this is the normal here and this is the cone. Okay, the rest is the cone. Now what I can say is that this is 90 degrees. That means the total angle will be alpha plus beta, alpha plus theta plus 90 degrees must be equal to 180, or this must be equal to 90 degrees. Also that means the normal is actually the normal. If you look at this normal, it is actually perpendicular, right? So perpendicular to the surface. That means x plus alpha must be equal to 90 degrees. So from that you can, theta, right? Theta is 45 degrees. Now substitute theta here and you can find out that x must be equal to what? Theta. Okay, so if you substitute that, you find out that alpha is equal to, I'm going to do it anyways, so it's 45 degrees. Substitute theta value, you get alpha is equal to 45. Substitute that here and you get x is equal to 45 degrees. Okay, that's a general case, and for a general case x is equal to theta. We found that out. Now you can use that. we can use that in the case of resolution. We have nx and ny here, right? So if you have a triangle like this, right, and this theta, then the x component and y component here, so x component or nx here must be equal to the n, which is the what, the hypotenuse, and nx must be equal to what, n times what uh, okay, nx must be equal to n times, okay, let's have a look at the angle. So cos theta will be adjacent, which is nx by n, right? So nx by n will be the cos theta. Similarly, sin theta will be opposite, which is ny by n. Okay, so now you can say that nx is equal to n cos theta and ny is equal to n sin theta. You got that? So we have resolved them into two components. Now if you look back into this problem, you see that there is the ball is rotating around in a circular motion, right, in a circular motion, just like that. So the centripetal acceleration here, which is m omega r, right? So m omega r is there, m omega square r is there. Now if you substitute that omega is equal to 2 pi by t, and earlier in the earlier problem, so it is almost equal. In the last problem we have did this, right? This is equal to mv square by r. The last problem, go back to the last problem if you want to know how this came out. So mv square r must be equal to the centripetal force, right? This is the centripetal force, the force that is acting in the radial direction. So that must be equal to, that is the centripetal force in the inverse direction, and the other force is normal nx, right? So nx must be equal to, this must be equal to what, nx. They are both in the inverse direction. So this is equal to, nx is equal to n cos theta. So n cos theta must be equal to mv square by r, simple. Similarly, n sin theta, which is in the y-axis, right? The y-axis, n sin theta. So n sin theta must be equal to the gravitational force here, right? The gravitational force which is acting downwards, mg. So with a minus sign. So n sin theta must be equal to mg, the minus sign. Now you can divide these both equations and you get n by n cancels, so you get I'm going to do sine by cos, so that is tan theta must be equal to, right, m and m will cancel, so you get g r, right, gr by v square, the rest will cancel, so you get that. So that's tan theta. So you can write down that r must be equal to, there's a minus sign but it shows the direction, so I am not taking care of that because I want the magnitude, the angle here. So you get r must be equal to what, v square by g tan theta, simple as that. So we found out r. So if you look back, our question was what will be the radius for two masses, 10 kilograms and 5 kilograms, right? So two masses, what would be the radius? So now you can clearly understand that it is independent for two masses, right? So there is no mass in this equation. So basically we have v, so v is equal to 10 meter per second, so that is 10 square, that is 100, and I'm going to take g as 10, okay, approximating 10. Tan 45 is 1, so you get 10 meter per second, sorry, 10 meters, so that's the radius. Okay, so that's the radius, very simple. So 10 meters was the radius. Even though the masses are different, they will always be 10 meters. So that's a very non-intuitive, you cannot imagine this just out of your hand. Okay, you would think that mass would make an effort and make an attempt to change this. So that's first problem, and now I'm going to give you another problem. Okay, So let's do another problem. This problem is like this. So you have a turntable, okay, with a center of axis. So this is going to rotate, right, in this direction with some omega, okay, some angular velocity omega, and there is a coin in here, or a box in here, there, okay, and the surface has some friction mu, friction coefficient of friction mu, and it has some mass m, okay, and it is some distance r from the center. All right, now I need to find out, what I need to find out is what is the minimum angular velocity omega, so that this thing doesn't fall off, right? How fast can you go around? Okay, that what is the maximum angular velocity? How fast can you go before this box is going to slip off? Okay, if you can do that, pause this video right now and you do that problem, or just continue with the video. So now I'm going to do this. I'm going to take the box anyways, and then define the contact forces here. So the first contact force is the gravitational force here. First force here is gravitational force, which is mg, and then there is a normal force n. There's a frictional force, right, acting on the surface. It is in the opposite direction of motion, so let's call that f friction, static friction. And then there is the inverse force, acceleration force, because of the rotation. So that is mr omega square, right? Mr omega square, simple as that. So now what I can do is that I can just say that, now what I'm going to do, I'm going to write down the solve the force equations. So first one is n must be equal to, in the y-axis, must be equal to minus mg, which is the opposite direction, and the x-axis you have minus fs or fs plus fs, frictional force. In the same direction there is centripetal acceleration force, so that is mr omega square. Okay, simple. Now what I can do is that I can now friction is what? Friction fs is equal to normal times mu, right? So normal is equal to minus mg. So normal is equal to minus mg, as you can clearly see. Okay. So n must be equal to, so fs must be equal to mg with a minus sign times mu. Okay. Now substitute that back into this equation. Okay. So you get the fs, which is minus m mu mg must be equal to m r omega square. M and m will cancel, so you get omega must be equal to square. I'm taking the magnitude here. Okay, direction is gone. We need to know what the direction is. Okay, so it is anti-clockwise, which is given anyways. So omega must be equal to mu times g by r. Okay, simplifying that, m and m will cancel. So we found out the omega. So if you have a static friction, which is some half, right, times 10 g, and it, so and the r is equal to say 1 meter, so r is equal to 1 meter, and you have static friction mu of 0.5, and g of approximately equal to 10 meter per second square. You substitute that back into this equation, right? So I'm not going to do that anyways. If you do that, you get a number, so you can clearly see that it depends inversely proportional to the radius, square root of radius, and it is directly proportional to friction. So how fast can you go, how fast can you rotate, is directly dependent on the frictional coefficient and the gravitational acceleration. If the higher the gravitational force, the stronger, the faster you can go. And if the radius is larger, it is actually very hard to keep it in place. So that's very non-intuitive, and I think this benefits you. Anyways, I'm going to stop this lecture here. and did two problems, and give me your feedback, and please subscribe the channel.